Everyone, another day, another DSA concept. So today we're going to be looking at Dijkstra's algorithm. So yeah, we'll just kind of go through a bit of the definition, when we should use it, when to use BFS or when to use Dijkstra, and then yeah, we'll just go through an example to see how it works. Okay, so what exactly is Dijkstra's algorithm? So it's an algorithm which is used to find the shortest distance from one source node to all other nodes in a weighted graph, a weighted directed graph, which does not have negative weights. Okay, so when are we supposed to use it? So the conditions are the graph has edges which have weights or costs, however the problem has defined it. So it's for problems where you're asked to find the minimum cost, the minimum distance, or the shortest time. Very quantitative kind of graph questions where you know you have to kind of minimize something. And yeah, obviously all the weights have to be greater than or equal to zero. So yeah, positive weights. Examples for this could be cheapest flights, shortest road distance, minimum travel time, least cost path in a game, a map. So yeah, this is normally if you're given like a network or a map and you're asked to minimize the distance and you have like different costs per distance, then this is a great example. But we're going to be solving problems, so I think you guys will understand at that time. Yeah, so the limitations, as I mentioned earlier as well. So it does not work when we have negative weights. So a negative weight actually breaks the core logic of Dijkstra, which is on like a greedy logic. So essentially we start going in a loop and yeah, so we can't really use that. I think we get a TLE for that. So in that case, you're supposed to use Bellman-Ford when you have negative weights, and you also want to find the shortest distance. So Bellman-Ford is something we'll also be looking at, but in another lecture, obviously. Okay, so let's see the difference between BFS and Dijkstra and like when we want to use which one. Because when I started solving problems on graphs, this was definitely something that took me a little while to wrap my head around. It comes with practice, or else you find it a little confusing if you solve a lot of problems initially and you like you're not getting the intuition as to solve what when. So let's see. Okay, so use BFS when the graph is unweighted, or it could also be a weighted graph, but all the weights can be the same. So yeah, if all the edges have the same weights, the same cost, then yeah, you can still use BFS. And why does it work in that case? Because every move costs the same. So basically, if I want to go from one place to another, it's like saying what are the shortest number, like what is the smallest number of edges that I can cover to get to that place. So essentially the problem goes from shortest path to actually minimum number of edges, which is what I've written over here. And as we know, the time complexity is v plus e, and this takes a q, so vertices and the total number of edges, and this uses a q. And what's different in Dijkstra? Okay, so we use it when our edges have weights, right? So edges have weights, and why does it work, right? Okay, so because now if I try to use a BFS approach, fewer number of edges does not really guarantee that I've taken the minimum cost to reach a node, right? So yeah, fewer edges does not always mean a smaller cost. And the time complexity is v plus e times log v. So it's actually v log v plus v plus e log v. Okay, so this is because we're using a priority queue, a heap, and a push and pop operation. If we take all of that into accountability, this is the eventual time complexity. We'll see that later while we're solving the problems. It's more intuitive. Okay, so yeah, here's kind of like a reminder that we can keep in mind. So BFS minimizes the number of edges, and Dijkstra minimizes the total path cost. So here's a small example of like how BFS can be used and how Dijkstra can be used and like why. So if I look at this and A is my source and D is my destination, I see that one of the shortest paths I can take is I can go from A to B, and I can go from B to D. And because there is no weight, there is actually no cost. But here the cost is basically the number of edges I took, so it's 2. So I can also go from A to C and then from C to D. And again, that's 2 edges. The same here, it was 2 edges. So that's 2. And both of these are minimum paths, and they both can be returned as answers, actually, either one of them. So yeah, BFS works here because all the edge weights, the costs are the same. And why do we need Dijkstra? Okay, so now we have a weighted directed graph, right? And let's look at the same thing. So A is our source and B is our destination. If I look at the same path that I took earlier, A to B to D, my cost would be 1 plus 1, and my total cost here is 2. So if I look at the other path that we had from BFS, it's A to C to D. And as I can see, A to C takes 10 and C to D takes 1. So that's 10 plus 1. And then I have my cost to go from the source to destination is 11. So now let's say I'm going on an airplane and I want to go from one place to another. Why would I pay extra to go, right, when I can go in a lesser amount? So this would be the optimal answer, A to B to D. And 2 would be the minimum path cost. Okay, let's just check out an example so things actually stick and we understand how Dijkstra is implemented. Okay, so I'm given a graph over here. I actually haven't drawn these. Okay, let's just say these are the directions, right? Okay. So the first thing that I do is that I initialize a priority queue, and we have to have a source, right? So in this case, A is our source, and we're gonna keep a distances array. So basically distances here, we're mentioning nodes as kind of these letters, but it would essentially be numbers. So distances would represent each of those nodes. And what I'm going to update for distances, all the distances are initially infinity except for the source, which is 0. And then I try to minimize the distance from that source to every other node. So my heap, my priority queue, initially will have the value of 0 and A. I'm starting from A with an initial distance of 0. And then I pop this out. I have A, which was at a distance of 0, and I look at the neighbors of A. So I have B, I have D, and I have C. And now I look at A to B, okay? So it took me 0 from A, and as I can see, to B, it's actually 4. So 0 plus 4 is giving me a value of 4. And then I go and check the distances of B, and that was infinity. So this is obviously smaller than that. So I go and update that. To 4. And here to my priority queue, I'm going to go ahead and add, it takes a distance of 4 to reach B from the source node. Okay, then I'll look at A to D. So the distances of A is obviously 0, as we can see. And so 0 plus to this edge over here is taking 7. So 0 plus 7 is equal to 7. And I look at the distances from A to D, and here it's infinity. So I'm going to rub this off and update this to 7. Okay, let me add that over here. So it's 7 to reach the node D. And A to C, 0 plus 1 over here. So this is 1. And again, I'm going to go ahead and update this to make it a distance of 1. All right, and add this over here. So it takes a cost of 1 to reach C. Now, my priority queue is going to pop out the smallest value here, right? As in the nearest node. So it pops out C, which took a distance of 1 to reach C initially. And I look at the neighbor of C, which is D. So the distance it took to reach C itself was 1, and the distance for C to go to D is also 1. So 1 plus 1 is 2. And then I go and check. So this is called relaxation, that step. So I go and check what was the actual distance to reach D initially, and it was 7. And now I've found a path which costs only 2 to get to D. So that's where I go and update this, and I make it 2. Yeah, so I've actually minimized this, and I've covered all my edges, everything leading to the other. Actually, I would have gone from pop this out later, and that would have been B at 4, and we can see that B has a neighbor. B has a neighbor D, and again that would have taken 4 plus 2, which would have made it 7 again. But we've already found 2, so that's the optimal answer. Okay, so what we do is we return this whole distances array if we're asked to find the shortest cost path from the source to all of the nodes. But if we were just asked from like A to D, a specific source and destination, we would have returned 2. Yeah, that's how it works. Okay. So the core idea, as we saw, is you always expand the node which currently has the smallest distance, and our priority queue basically takes care of that. And I mentioned a term called relaxation. So relaxation was basically that process which we were doing, where we took the current distance from that specific node, we took the edge weight to its neighboring node, and we checked that if through this node, if I'm going to my neighboring node, is it costing me less than what another path had taken to reach that neighboring node? So that's where old distance is. And if that's the case, then we just go ahead and update that old distance to the neighbor. So yeah, this is how it's written, and in the code, that's basically what we do. So yeah, that is Dijkstra's algorithm for you guys, and it's sort of, I mean, even now, I guess, sometimes I get a little confused, like what I'm supposed to use where, because graphs is essentially a topic where we have a lot of algorithms and a lot of methods to solve stuff. So sometimes the terms are a little confusing. So yeah, I kind of wrote this out for that. So if you have an unweighted graph, you can go ahead and use BFS, unweighted graph, or you have a weighted graph, which has like all the edges have the same weight, so then you can use a BFS. If you have a weighted graph, then you can go ahead and use Dijkstra. So if you have negative weights, you can use Bellman-Ford, which we will be seeing in the next lecture. If you have a directed acyclic graph and you want to look for the shortest path, then you can go ahead and use topological sort. And if you want to find multi-source shortest path, so here we were looking from the source A to all other nodes, but if I want to go from B to D, if I want to go from A to D, C to D, or B to D, or C to B, or all these combinations basically, then I would go ahead and use Floyd-Warshall's algorithm, which is also something we will see in another lecture. So yeah, that's for multi-source shortest path. And if you want to check connected components in graphs, or like if you want to club components, like different nodes together to check for the component, then you go for disjoint set union, Kruskall's algorithm. And then minimum spanning tree, again, we will discuss in another lecture. You go ahead and use Prim's algorithm. So yeah, I just sort of wanted to write this down somewhere. So yeah, that's why I've done that. But I hope you guys understood this. And yeah, so let's go ahead and solve some problems with Dijkstra in the coming videos. So yeah, happy coding, everyone.